My name is Lars Jorgensen. I work for ThorCon Power. We're a startup with just 5 or 6 people, so we're not a big corporation yet. So this line here shows you what the EIA has tracked for worldwide electricity consumption and their forecast for the future. And then the black line is how much is satisfied by fossil fuels, which primarily means coal. And as you can see, coal dominates. Not only historically, but dominates right up to present day. EIA is kind of hoping that maybe coal will dominate a little bit less in the future, but I think honestly that's a hope. It won't change unless we do something to change it. Here, this is gigawatts electric. So one large nuclear power plant is roughly a unit of 1. So this is roughly equivalent to how many large nuclear power plants do we need? In Europe and the US, we use about 1 kilowatt per person. In Europe and California. US is a bit higher as a whole. Reasonable efficiency gains, we should be thinking along the lines of 1 kilowatt per person. Our current population is 7 billion. It's probably going to grow to in the neighborhood of 10 billion before the economies grow big enough that population stabilizes. So we're looking at a market of about 10,000 gigawatts electric. But it could be larger because while we may not be in peak oil, we keep looking harder, we keep finding more, but I don't think anybody honestly expects we're going to find 5 times as much oil as we have. So transport is going to shift. Likely it's going to shift towards electricity. That's going to drive up our demand and how much total generation we need. Similarly with industrial heat. So there's a lot of reasons to suspect that 10,000 gigawatts is still a pretty low ball estimate, and we might be looking at maybe as high as 70,000 gigawatts electric. This is a huge, huge market, the size of the whole oil industry today. If you look around to say what could possibly supply this kind of energy, nuclear is the answer. The others simply can't meet that demand. But if we don't change the price of nuclear, we're going to be dominated by coal. And you're going to see 10 times as much coal as we have today. That's what's going to happen unless we can create a nuclear that's cheaper. The good news, though, is that most of this nuclear is going into greenfield deployments. It's going to people in the world that don't have electricity yet. So we've got kind of a level playing field of brand new coal versus brand new nuclear. That's a lot easier battle to win than an existing coal plant and I want you to shut it down, I'm going to replace it with a nuclear plant. That's a hard economic argument to win. To successfully compete against coal, we need something that can scale up to a very high volume, on the order of 100 gigawatt per year installation. Not 2 or 3, but around 100 gigawatts per year, or you're not seriously competing with coal. That sounds scary. I mean, it's a lot bigger than we've known how to do so far, but this is roughly what we're doing for wide-body aircrafts. Between Boeing and Airbus, they've already produced 100 wide-body airplanes this year. So it's on that kind of manufacturing scale. It's not really out of sight. But we also have to be extremely safe. If you're going to have 10,000 operators out, nuclear power plants out there, your skill level is not going to be all ex-Navy nuclear operators. Your skill level is going to drop, and our safety record is going to be set by the bottom 10%, right? So we need a reactor design that is extremely safe. Not just passive decay heat removal, but it has to be safe in other ways that operator screw-ups or management orders to the contrary can't really do harm beyond destroying the power plant. And we have to have it in a way that we convince people, convince general population, not nuclear enthusiasts, that this plant isn't going to destroy their city. If we're going to compete against coal, it has to be lower cost. You can't have a price premium because the market you're serving is people who are coming out of no electricity. And even if they understand that coal is nasty, it's better than no electricity. Drinking river water is a lot more dangerous than drinking groundwater, and you've got to get your electricity to be able to pump it. It's a matter of life and death for them, and they don't have any extra money. So if you're not cheaper than coal, you're not going to make it. So our target is 3 cents a kilowatt hour and $1 a watt for capital cost. The other thing is we want it soon, because it's a lot easier to compete for a greenfield deployment than to compete against somebody who's already got an installed plant and you want them to turn it off and replace it with this new coal plant. Soon is very, very important. So we don't want to do something that's even better, but 10 years later. So our goal is driven by what can you do now and get started, get going, because anything nuclear, frankly, is better than coal. So if we can make the cost and we can get there and get in the market, then we can fuss about reducing waste in the future. So to go to more detail on the volume production end, this picture is a picture of an ultra-large crude carrier. It's one of the world's largest ships. It was actually designed and built by the founder of our company. This blue box here is a 1 gigawatt power plant. So drawn so that you can see it head on. This is a 1 gigawatt nuclear island of a power plant, not the turbines and the generators and the cooling towers and stuff, but the nuclear island. And it's small compared to the boat. It's like 1/4 of the steel. And similarly for virtually all the other numbers here, which are too much to go through. But it's simpler to build and 1/4 of the steel. This boat cost $90 million. So if I can build a 1 gigawatt power plant for anything remotely resembling how much it cost us to build that boat, that ship, then we're doing very much better than with current technology. The reason that it costs so little for that boat compared to how big it is that they have shipyards that run things in production. This is for a double-hulled ship. You've got a plate of steel on the bottom, you've got ribs going across here, you've got robot welders that are welding the ribs to the plate of steel, and you've got one person there running 5 or 6 different machines simultaneously. And then they flip it over and they do the other side, so you make this double-hulled construction. We're building the power plants using the same basic technology, actually in the same yards. So our power plant basically is a boat dug into the ground with double-hull steel and concrete poured between the steel. One nice effect of that is that you get very high quality control. You get a lot more uniformity, a lot tighter quality control. We do these in blocks that are 150 to 500 tons, and the blocks have to align in the field very precisely, and then they're welded together. We do the measurements, and they're quite accurate on those measurements. They have to compensate for how much 2-inch thick steel sags when it's set on end. We can do the full inspection on the production line, and if there's any defects, you can reject the block, do the modifications on the production line. You don't have to do this work in the field. So our goal is to get like 90% of the work done at the production line and leave only 10% for the field. A 1 gigawatt power plant is about 100 of these blocks. So they're pre-coated, pre-piped, pre-wired, everything is all finished in them, and they're ready to basically plug like Lego blocks to the adjacent blocks. Once the blocks are all ready, in a normal ship, they would be built in the dry dock at the shipyard. In our case, we're going to put them on a barge and carry them out to the nuclear power plant site. This picture here is of a shipyard in Korea, run by Hyundai. This is actually the world's largest shipyard. The highlighted area is the area we would need to build a 10 gigawatt per year power plant factory. And this gives you actual dimensions on it. If we took up this whole shipyard, we would be able to produce 100 gigawatts per year. So the concept of being able to build power plants at 100 gigawatts per year is very, very much viable. And once we get away from the thick forgings of the reactor vessel that you have with light water reactors. The block size is limited by the transport. We would love to build the whole power plant in one big block. It gets to be a little awkward to carry around. What we notice is that about 80% of the world's population lives within 500 miles of a coast or a major river. So we're planning to use barges for our transport, which makes it so that we can transport these 500-ton blocks. They can be much larger than you can fit on a truck or a train. And that makes it so that we can do more of the work at the factory, do more of the inspections at the factory. So the barges are up to 23 meters wide. That's set by a lot of the rivers and the locks in the river systems. 500 tons is our current design limit, but that's set by crane sizes, and there are larger cranes, so we're going to be doing some economy trade-offs of whether we should go to larger blocks still or not. So the concept is you have a factory that puts things onto a barge. Takes us about 20 barge loads to deploy a 1 gigawatt power plant, so that's what this is. And once you've done that, then every 4 years we exchange our cans, because we have a graphite moderated reactor, and so the graphite is going to get neutron damaged. We have to replace it. And we do that by having sealed cans that we put on a can ship, we call it, a specially designed ship, that will haul those back to a can recycling center, which is basically looks like another shipyard that services about 50 gigawatts electric. And we take the cans in, clean them, inspect them, make sure they're still good to go, ship them back out, or in some cases, like with the graphite, we take the old out and put the new in. After we've been doing that for a decade or so, we're going to have some spent fuel, and that will go to a fuel recycling center. We'll start out with just using simple fluorination and distillation to recover most of the salt. That'll let us recover the salt and the uranium and the thorium. It does not let us recover the transuranics. Future, we would anticipate making this a secure site and being able to do re-enrichment and to do the transuranic extractions. Power plants are quite content to eat all of their own transuranics so that our waste flow as far as the plutonium and curium and americium is set by how much leaks through your chemical extraction process. We have to be safe. This is a 1 gigawatt power plant site. We have, you see the can ship here. You see this little red one is a can. That's a 250 megawatt electric reactor. We have a crane that moves along on rails, so a gantry crane that picks it up and takes it over. These yellow hatches here are the doors to our reactor. So our reactor is completely underground, and you access it directly from above. So you take off the trap door and then you lower the reactor down into it. These closed towers here are the decay heat cooling towers. So we have fully passive decay heat removal. And then this is a standard turbine generator. We use standard steam cycle turbine generators until other people spend the money to invent the Brayton cycles. We have no objection to Brayton cycle, but we don't want to wait. I can buy the steam cycles today, and I want now. Then behind that is a switch yard and forced draft cooling. But I'm sure we're going to end up having to support several different cooling styles depending on the site. So this just gives you some of the dimensions in meters of the different areas. Optimum turbine generator set is about a 600 megawatt turbine generator. They make them larger, but they don't get any cheaper per megawatt, so we get better modularity by going about 600. They make them smaller, but they get more expensive. So we're sticking around the 600 megawatt. We have 250 megawatt blocks, so it takes 2 of those to drive it, and these little red lines here are the steam lines that are going off to the turbine generator building. The nuclear island itself is 250 megawatts. We have 2 cans, so we're duplexed. So one can is operating while the other can has spent fuel in it and is cooling down, letting things cool down before we transport it over the ocean. So what we're transporting is on the order of 4 years old. Okay, each can contains the primary loop pump, the primary heat exchanger, and the reactor vessel itself. And so all of our radioactivity is really contained within the can. We ship a sealed can out, we take a sealed can back. Inside the can, you've got the reactor vessel called the pot. We've got the pump and the primary heat exchanger, and those go around in a loop. You get secondary salt coming in and going out. And we have the fuse valve here at the bottom. And this will go off to a fuel dump tank, which we'll talk about in a minute. Everything is hung from the ceiling of the can to accommodate the thermal expansion. That turns out to be a reasonably challenging engineering problem. How do you deal with how things change shape as they go from room temperature up to 700 C? So we've done that by hanging everything from the roof and letting the cables adjust to let the parts move apart from each other and squeeze together with temperature. The pump is moving about 1 cubic meter, about 3,000 kilograms per second, and it's about 14 seconds to go around the loop. And you only have one major part, that's the impeller for the pump, and the pressure is modest. The pod itself is around 4 atmospheres. The highest pressure in the loop is 12 atmospheres. So we're dealing with very modest pressures here. At the bottom, below the can, we have what we call a fuel dump tank. And it's just the green part. It's a donut-shaped vessel that will hold all the fuel salt. And because it's donut-shaped, it's very poor for neutronics. Because we can move the fuel, we move it there, and it's in exactly the wrong shape for good neutronics. So the reactivity down there is very low, and if gravity works, anything overheats will cause something to melt, preferably the fuse valve, but if that fails, then a pipe will melt, and the fuel salt will fall down into this donut where it is not going to fission. Guaranteed. No chance, no discussion about possible recriticality. That just isn't possible to happen. Around this, I should say also that the fuse valve and the emergency drain here is something that the operator can't prevent. If the Prime Minister calls and says, no, you're not allowed to open the valve, the operator just says, I can't stop it. There's no valve he can possibly fail to open. There's no valve he can accidentally leave closed and cause trouble with, like we had with 3 Mile Island. So the safety here is not operator dependent or Prime Minister dependent. The next safety feature is what we call the membrane wall. These are vertical pipes, this is the dark blue here, that surround the can and the fuel dump tank, and they're filled with water. Heat radiates from the can to the pipes. If the pipe gets over 100 degrees C, it changes to steam, and that wants to float. That creates a natural circulation. It's a very strong pump. So we have radiation going from here to there that will keep the can temperature at around 270 C. And likewise, if you get down to the fuel dump tank, if we have the heat generated down here, then it'll pump up from here. So the decay heat removal is there all the time. It's operating all the time. If something should happen, if, I don't know, some earthquake squeezed a pipe or something that blocked it, we will know because we see it in the flow during normal operation. We don't have to wait for the tsunami to hit to discover we have a problem. So we have it continuously being tested, continuously running, and the operator has no valve, nothing he can do to stop it. It also doesn't penetrate any of the radioactivity area. So this is done purely by radiation, no bayonets or anything probing down into the fuel dump tank. So we've tested this in software up to 30 megawatts of power decay heat, and the peak decay heat we actually see is 5 megawatts, so we have a lot of margin on that. Once we get the heat into the water of the membrane wall, we got to get it further away because there's only so much water there. So what happens is the hot water travels over here to a pond. The pond evaporates and goes up to this steel cone above it, chimney, which is air cooled, and so the water condenses on there and falls back down again. That should give us nearly infinite supply of decay heat removal. If for some reason you're not allowed to put a chimney up, then it's still 72 days worth. So we have plenty of decay heat removal, and this is atmospheric pressure water, so it's very easy to replenish the water if you have any need to. Besides decay removal, we have multiple barriers to removal to the radiation. The radiation is inside a primary loop, the pump, the pot, the pipe. So it's inside here. That is all inside of the can and the fuel drain tank. So that's the second barrier. The can and drain tank is in something we call a silo, which is a concrete structure, basically a concrete cylinder can that's concrete steel cylinder that's also gas type. And then that whole thing is inside of what we call the silo hull, which includes the motors and the hatch to the outside world. So this is where you finally get to the outside world, and this is all ground underneath. So we have 4 barriers to getting any kind of radioactive release, and at least 1 barrier between adjacent modules. So if you did have one module that goes out, it's very unlikely to contaminate the adjacent modules. We actually, in many ways, have a 5th barrier in that the fluoride salt itself is a very good barrier in that the dangerous nuclides or elements would be your cesium, your strontium, and your iodine. And the cesium and strontium form pretty tight fluorides that don't want to go anywhere. In fact, figuring out how to get the strontium out is a fair challenge. It doesn't even boil until like 2500 C or something ridiculous. So even if somebody sent, say, a bunker buster missile in and went blasting through all of the barriers, you create a spill, it's a spilled salt that solidifies on the floor. It's not something that wants to go into the atmosphere in the first place. Just a quick word on the neutronics. I'll keep this real short. The core is made up of logs. The logs are made up of planks, and all of that is graphite. If you're familiar with the Ebesco design, that was a spin-off from MSRE when they were looking at MSBR, it's based on that. We've made an accurate 3D model of the pot and run that both through MCMP and Serpent and get consistent results through them. So we're pretty confident on that. We've actually extended the model to include a fair portion of the power plant beyond the reactor vessel itself, so we can see what about radiolysis of the membrane wall water and other questions like that. We're able to handle fairly flexibly what kind of fuel and salt in the same reactor. We're currently planning on using NABI, sodium fluoride, beryllium fluoride as our baseline salt because we can buy it now. FLiBe is a little harder to get by, and we don't want our schedule to be dependent on when we can buy FLiBe. So we make the economics work with NABI. When FLiBe comes along, we can switch to it. Likewise, what enrichment we can start with depends on time. Okay. So early on, we're thinking we might be stuck with 3% or 5% uranium, and then later on, we'll be able to switch up to 20% and get better efficiency, better economics. But it just changes the economics by less than a penny per kilowatt. So it's not a super critical thing. So also need to be lower cost than coal. I want you to just notice the turbine generator building here and get a picture of that in your mind. I'm going to derail for a second and talk about should cost versus did cost. Should cost would be, if we set up a manufacturing line, how much does it take based on putting in the materials and the skills we have to put in, the labor we have to put in. Did cost is, and then what happened when you got in with all the regulations. So we're going to focus on what it should cost. The regulations are going to come in on a country by country basis, and it's going to preclude us from certain countries until they come to their senses. That turbine hull that I showed you in the picture before, this is the one turbine hull for a coal plant of a similar size. It dominated ours, and in the coal plant, yeah, it's there someplace. So competing against coal doesn't have to be that hard. And they've got the hard job. They've got the guys that are going to move 10,000 tons a day. They've got the guys that got 10 times as much building as we do. We should be able to beat them, and we can. So on steel, we got roughly 1/5 the amount of steel as a coal plant does. For concrete, we've got about 1/3 the concrete that the coal plant does. So our materials cost should definitely be significantly lower. We do have some exotic materials, so that adds up to about $100 million per gigawatt. So if we get to the levelized costs, I can go through all the details here, but bottom line, talking about roughly 6 cents a kilowatt hour for coal and about 3 cents a kilowatt hour for ThorCon. It's roughly where we think we're at. The other thing we think is important is if you're going to have 10,000 units deployed, inevitably some of them are going to break. We can't say why, we don't know where, but something's going to break someplace sometime. And we want to be sure that that is not a significant event. So all the modules are replaceable, and you have hatches on the top that lets you come in, take the module out, put a new module in. That's quite different than existing light water power plants where they have to deal with these very large pressures and large inventory of steam, of water that could turn to steam and has to be contained. Because then you have to cut through the concrete mausoleum to try to get in there to fix things, and that can be quite expensive and has actually ruined some power plants. And finally, it's to get it ready now. So we've started with MSRE, and we've made sacrifices in neutronics performance, somewhat in economics performance, in order to keep the schedule short. So we're not depending on when we can get lithium-7. We're saying we can do just fine with NABI. We're not depending on when we can get around to processing the plutonium and extracting it and recycling it. We'll say, it'll wait for us. We have some spent fuel, we'll stick it over there in the corner. When we finally get that process ready, we can go back and clean it up. It's not going anywhere. We're not going to go with the Brayton cycle because it's not here now. We can go buy steam power plants and compete with coal now. We do plan to build a full-scale prototype. So our prototype will be 250 megawatt electric. And once we've tested that and abused it and made it go through all accident scenarios so that we can tell people in the city, no, we know this, no danger is going to happen because we've tested it. We've actually done it. We'll ruin a power plant in the process of doing that testing, but we'll be able to give people that reassurance, that safety. Okay, we think we can get pre-fission testing in about 2 years and to fission testing in about 4 years based on the speed of technology of how fast we can get the work done. Now you have to add to that, if the regulation system is slower than us, then it'll extend the period. We have some countries where we think we could just add 1 year to that period, schedule and work in those countries. The other one is going to be the finance, which I don't have answers for it right now. That kind of schedule seems kind of crazy to people used to the nuclear industry, but I'd point out that Camp Century was built in 2 years. The Nautilus was built in 6, and that was the very first one and had lots of extra challenges being a submarine and all. Hanford was built in 2 years. It's, by those standards, ours is a rather lax schedule. So this sets out the schedule out to full manufacturing, factoring deployments and where we think we're going to go. So roughly a decade we think we could be in volume production. Okay, questions?
Your construction costs are $1 per watt, correct?
Yes.
What is right now a typical power plant?
For nuclear power? What, about $8 a watt in the US and $6 a watt in UAE, something like that?
5, 6 in China.
Yeah, 5 or 6 in China. Yes.
With that $8 in the US, is that a lot to do with regulation? Very significant cost, or?
A third of it is attributable to regulatory.
Okay, the question is the $8 in the US based on regulation? And the answer is partially.
Yeah.
Partially it's the fact that it's a light water reactor, so most of the construction happens on site, and therefore you don't get the benefits of having an assembly line. Partially it's the very thick concrete structures and lots of rebar that is expensive to build.
How big is your team, and what is it going to take to reach your goals financially?
Our team right now is about 6. We're looking at roughly 10 million for the initial design to get through bids, get bids from subcontractors ready, 10 million. And then about 100 million to get the pre-fission prototype tested, built and tested, and about 700 million to get the fission prototype tested.
How did you make the decision between operating as a company that sells reactors to utilities versus being a company that owns reactors and sells power?
I don't think we've made that decision, and I think that will probably be made by the guy that comes up with the $700 million check.
Well, thank you very much. Thank you, Lars.